two ways in this section that we're going to utilize the idea of a differential, one of which is we're going to talk about the idea of how much a function changes over a given interval. So if we have an initial value, x0, and we have a terminal value, x1, what's the value of the function changing? There's two ways that we're going to be able to figure that out. One of which is going to be the exact value, which we call delta f. So it's our exact value. And that's just going to be the function at the terminal value minus the function at the initial value. We can find the approximate change by just taking the derivative, but then also multiplying it by the change in x. All right, so dx is going to be that change, the delta x, which is going to be x1 minus x0. So let's see how good of an approximation we can get by using the differential for this. So we have a basic quadratic function, and we're going to change that function from x equals 1 to 1.04, compute the exact change, and then compute the change using a differential, and then we're going to find the percent error. So first part's easy. Delta f is going to be equal to, in this case, f at 1.04 minus f at 1, which is going to be equal to our 4 minus 2 times 1.04 square minus 4 minus 2 times 1 square. And the 4s are going to go away. And so we're going to be left with negative 2 times 1.04 square plus 2. We could just throw that in our calculator to be able to compute that. So we're going to say 2 minus 2 times 1.04 squared. And we end up with negative 0.1632. All right, so that's the precise value. All right, so that's our delta f. Now, how do we get an approximate? So what we're going to do is we're going to find the derivative. All right, so we're going to say that f prime at x is going to be equal to the derivative of this function, which is really basic. It's negative 4x, but then we're going to multiply it by this dx for our differential. All right, and now in this case, the differential is just going to be terminal minus initial. All right, and we're going to substitute the initial value back in for x. So in this case, we're going to get negative 4 times 1, and then we're going to have 1.04 minus 1. All right, and we know that that's just going to be 0.04. And we could probably do this in our heads if we really wanted to. So this would probably work out to be negative 0.16, but let's just use our calculator just to be certain. So we have negative 4 times 1, which we know is going to be 4, and then times 1.04 minus 1. Let me try that again. So we have 1.04. Let's clear all of it out. So we had negative 4 times the quantity of 1.04 minus 1. And that's negative 0.16. All right, so now that's our differential, which is the approximate. This is the exact. Clearly, they're really close to one another. Let's find that percent error. Okay, so percent error is going to be equal to our estimate, which is our negative 0.16 minus a negative 0.1632. And then we're going to divide that by 1632. All right, so we'll just throw that in our calculator. So, and remember, everything's going to be positive, so it doesn't matter what sign we have. So we're going to have 0.16 negative plus 0.1632. And then we're going to divide that by 0.1632. And we end up with, and we're going to multiply that by 100. And so we end up with 1.9608 or 1.96078%. Okay, so we have to multiply that by 100%. And the percent error for this is going to be 1.96078%. All right, so not that bad. All right, by using a differential. Now, clearly, this is a really easy function to be able to consider. However, if we started using more complex functions, then it might be useful for us to use the differential as opposed to actually finding delta F. An applied problem. Let's approximate the change in the volume of a sphere when its radius changes from r equals 20 feet to r equals 20.05 feet. And we're given the formula that the volume of the radius of the sphere is going to be 4/3 pi r cubed. So just like we did before, we're going to find the differential. And certainly we could find the exact value by plugging in 20.05, subtracting out 20. But let's call this v prime of r. And that's going to be 4/3 pi. And then when we take the derivative of this r cubed, that's going to be 3r squared. But then we have a dr in it. All right, now clearly this is going to cancel out. And so what we're really left with 4 pi r squared dr. We know that the initial value of the radius was 20. And so this is actually going to give us the change in the volume of the sphere. So this is going to be, it's similar to a related rate problem that we did earlier in the course. So this is going to be 4 pi times 20 square. And then the change in the radius is going to be terminal minus initial. So 20.05 minus 20. All right. Now our answer is going to be in feet cubed because we're changing the volume of the sphere. All right. So really what this ends up being is 4 times 400. So 4 times 400 times pi times 0.05. And from here, what we could do is we could just throw that into a calculator and get an approximation for this. Okay, so clear this out. And we have 4 times 400 times our 0.05. And then we're going to multiply that by pi. All right. And so we get about 251.327 if we were to approximate it to the thousandths place. So this would be 251.327 cubic feet. Okay. And whatever that change might be in. All right. So it'll be cubic feet per whatever the time might be. So second, foot, whatever it might, or second, or minute, or whatever it might be. All right. Another way to write this would be in the exact form, where we could just keep the pi in there. All right. So we have to be careful whichever way it wants us to write it. So 4 times 400 times 0.05. And that would be 80. So another way to write this would be 80 pi cubic feet. All right. So that's how much it's changing. All right. So hopefully this helps out a little bit with being able to understand where a differential might be useful. We do have one more example, and then we'll do that in our final video for this series.